Hi everyone, it's Judy. Welcome back to the OnTrack podcast. Today we speak with Mike Konrad, who's the founder and president of Aqueous Technologies. He's also my fellow podcaster, and he hosts a show called Reliability Matters. His passion is to educate people about the importance of cleaning your boards at assembly. And if you care about design for reliability, you're going to learn a lot from Mike today. And don't forget to check out the show notes when you're done listening. I'm going to share a lot of resources that Mike puts out there that you're really going to enjoy. I'll see you on the other side. Welcome to Altium's OnTrack podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Well, hi, Mike. Thanks so much for joining on our podcast today. This is like dueling podcasters. This is very fun for us to have you today.
Well, I'm excited. Thanks for inviting me, Judy.
I know. You're used to being a host. Who's going to interview who?
Could be the clash of the interviewers. I don't know. I'm looking forward to not having to ask questions and do the research.
Good.
Good. So I'm looking forward to being interviewed. It's a nice switch,
right?
The table. Yeah.
Okay. Well, why don't you start off by giving our audience a little introduction to your professional background, and then tell us a little bit about Aqueous Technologies.
Sure. Well, I started in this industry, the electronic assembly industry, in 1985 when I was 24 years old. And I just kind of fell into it. There was a sales job and offered, and I'm like, oh yeah, sure, I can sell anything. So I thought, at 24, you can do anything.
Right.
So I started in this industry, and I worked at a company for 7 years. And while I was there, that was right in the time of the Montreal Protocol, and I think we're going to get into that in a little bit. So before I dive down that rabbit hole, I'll finish answering the question. So I worked there for 7 years selling soldering equipment and cleaning equipment. And then in 1992, I founded Aqueous Technologies 27 years ago, and have been just having a blast for the last 27 years.
So tell us a little bit about Aqueous. You know, we're talking to EEs and board designers here mostly. Me coming from the fab side, Aqueous is one of our go-to words, right? But tell us a little bit about what that means.
Sure. We build machines that clean circuit boards. We do a little bit more than that, but our primary emphasis is to manufacture, sell, and support machines that clean circuit boards after reflow. So we're further down the river than your industry is. Mm-hmm. You know, take your boards and our customers populate them and reflow the components on and rework them and do whatever they're going to do. And then in most cases, not all, but in most cases, they then remove all the sins of the process. They remove the flux, of course, which they intentionally applied, and then they remove all the other things which they unintentionally applied. And the conventional wisdom is when you remove ionic residues specifically, you eliminate the chance of electrochemical migration. So that's what our machines do. We've since over the years developed out cleanliness testers, rose testers, resistivity of solvent extract testers, and stencil cleaners using ultrasonic energy for stencils. And we do contract testing when we're forced to, but we're basically equipment peddlers. We manufacture and peddle equipment around the world.
Important equipment, albeit it is very important.
We think so.
Yeah.
It's funny. You can get away with not cleaning. That we learned in the late 80s, early 90s, when our government and 11 others, and since every government that's a member of the United Nations banned certain chlorofluorocarbons, CFCs, we thought cleaning was going to go away when no clean flux, necessity being the mother of invention, no clean was the offspring of the ban on the cleaning solvents that were being used to clean boards back in the day. Mm-hmm. And we thought cleaning was gone. We thought, well, okay, the military will clean, the medical people will clean, but everyone else will stop cleaning. And that was pretty much the case for a dozen years, maybe a little bit more. And now, due to all sorts of things which we can get into, people are coming back to cleaning again. And we're like, welcome back. We're happy to have you back. But cleaning is something that is optional. It's mandatory for some people. It's optional for others. But it adds reliability. It's an extra step that adds reliability to the assembly.
Which is the name of your podcast, Reliability Matters. So
great segue. Yeah.
I know, right? Yes. So let's talk about cleaning. Why? First of all, let's talk about silos. The silos we all live in, right?
Right.
You and I were chatting on the phone where, well, tell us about, your perspective, say, on fabricators, which would have been me some years back as, say, somebody who sells equipment to contract manufacturers or EMS companies. Like, how do you think they look at different parts of the supply chain or the designers?
Yeah, it's funny. We're all in the same pool, but we're at completely different ends of the pool. And in our industry, the electronic assembly industry, and I'm going to make a very stereotypical statement. I'm going to make a wide statement. There are many exceptions to this statement. But basically, my experience is we don't know a whole lot about the black art of fabrication, board fabrication. We just get boards mysteriously in the mail, and we populate them. And my experience is there's not a lot of information either available to or sought by assemblers for best practices in fabrication, how to choose a fabricator, even how to choose materials, why choose certain materials, why choose certain fabrication methods, etc. It's just this kind of black art. There's this building somewhere in the U.S. or China or anywhere in between, and then we place an order. We negotiate the best price for saving pennies per board, and then we get a board that we can build on. And from the fabrication standpoint, I think maybe that's the same when it comes to assembly.
It is.
A void of knowledge between assemblers and fabricators.
If anything, for fabricators, it's like, dang, they don't appreciate what we do. It's very complex. They don't understand. They think it's just a line item on their BOM, and they're always pressing us for price, right?
Price and delivery.
Right?
But fabricators do fill an important role for assemblers. They are a very convenient company to blame when things go wrong.
There's that.
Whether it has anything to do with fabrication or not. The go-to
Yes.
is your board's bad. Clearly, the
clearly, I know.
Whatever.
It all rolls backwards, right?
Back. So it rolls on us, and we keep moving.
Yeah, yeah. So, what do you think that sort of this condition of us living in silos, and you live in this really kind of niche-y part, cleaning. What? What does that mean for the way a circuit board might come in to an assembly house? Is it ready to just throw on the line and off we go? Or are there issues cleanliness-wise on the front end, and what are the impacts?
Yeah, that's a great question. Every board has a tolerance for residue. And that tolerance is unique to each board based on design, component density, climactic environment where the board is going to be in use, etc. And because each board has a different level of tolerance, it's difficult and actually impossible to predict what level of contamination that board will be okay with. So, because it's all different, it's all relative. So what we tell our customers is, your board can tolerate some degree of residue, clearly. Even in the harshest conditions, it can tolerate maybe a minute amount of residue. And in very controlled conditions, depending on other factors, it might be able to tolerate quite a bit of residue. You might have to clean it, you might not have to clean it. But what the factors to predict the residue tolerance really stem from the totality of residues that might be on the board. And that might be on the board when they receive it from the fabricator. It might be on the board as it travels through multiple thermal excursions, through reflow, through wave, through hand solder. It might be added to the board based on whether or not operators are wearing gloves, and whether those gloves are just put back in the pocket for months at a time. It might be affected by what I like to call the Dorito effect. After breaks and lunch, much ionic residue ends up on the board.
Yeah.
But never assume that the board starts at zero. Never assume that, because any board, no matter how much quality and care was put into the board fabrication process, the board fabrication process is, and I don't mean this I mean this in a respectful way, is a dirty process, meaning, it's a plating shop. There's all sorts of chemicals, there's all sorts of materials, there's all sorts of handling, and there's everything from particulate materials to ionic materials. Hassle finishes are completely terrible when it comes to entrapping residues. And, the board may not be completely clean when it's received and unwrapped and removed from the dry box and the cello wrap and all that. It probably has some level of contamination. So you're not starting at zero. So just assume that you're starting at something greater than zero. And if you have let's call it 1 to 100 or 0 to 100, 100 being the point where a board fails, you're probably starting around 10, which is not bad. If you don't add any contamination to it, you're fine. However, the assembly process is just as dirty in many ways as the fabrication process. And then contamination builds, and the totality of that contamination builds. And at some point, someone crosses the threshold. They end up with 101 or 102, which is a made-up number on a made-up scale. And then they have a problem when the board goes out into the field. So,
and what are the implications of a board that's not cleaned properly in the field?
The major implication would be ECM failures, electrochemical migration failures, which take the form of three. It manifests itself in three forms. One is dendritic growth, where actual metal crystals grow between conductors on the board. They grow between anodes and cathodes, and it's like sprinkling metal shavings on your board while it's plugged in. It's not a good thing. The board loses its dielectric properties, and it basically adds conductive material over insulating material and creates shorts on a board. That's the dramatic manifestation of electrochemical migration. A less dramatic, but actually more troubling manifestation of ECM is parasitic leakage. Parasitic leakage is a loss of conductivity, a loss in resistivity, a rise in conductivity, which adds a current path, but not enough to create a dead short. So if one has a board that is controlling a sensitive device, it might not calibrate. If the board is backed up by a battery or operated with a battery source, it might drain the battery quicker. Not enough to create a short, not enough to create a fire, but enough to cause the board to malfunction. And the troubling thing with parasitic leakage is the problem only exists when the conditions are perfect for it to exist. So there has to be electrical current, there has to be moisture, and there has to be some conductive material on the board. And when those conditions are perfect, the board malfunctions. When the board is returned to the manufacturer to determine what's wrong, the manufacturer is in a climate-controlled environment. The humidity is it's stable, and the board doesn't manifest the problem. So there are two acronyms which result from that. One is NTF, which is no trouble found, and generally that creates another one called WTF, which I'll let your listeners pick. So NTF, WTF, it goes back to the customer, no trouble found. The customer then, puts it back in the harsh environment. The trouble manifests itself again, and you can see this vicious cycle. The third issue with ECM is actually more related to board fabrication. The assemblers don't have a lot of input into this failure mechanism, and that's CAF, which is conductive anodic filament. And I like to add an extra F. I like to say CAF because I like to add the word failure to the end of it, because that's normally what happens. So conductive anodic filament failure. And that is that's partially caused by microcracks or dry weave between the layers of a board, where the plating solution from the vias and the through holes leached out into these little microcracks. These microcracks can be caused by multiple thermal excursions. It could be caused by too much pressure on the drilling when the boards are being drilled. It could be dull drills. It could just be inadequate resin flow within the laminate. It could be a number of things. And when the board is then under current, if the board has picked up moisture between the layers, which boards tend to do, then the moisture, you've got the three things. You've got moisture, and you have electrical current, and you have conductive surfaces from the plating solutions, because there's no way to wash those out from between the layers. And we get basically dendritic growth. We get metal crystals growing between anodes and cathodes, and that creates a short within the layers of the board. So those are the three manifestations of ECM that we see. In our business, we see that every day.
So let's talk applications for a moment. What does that mean? Like, for certain applications, say medical devices or military jets, or I don't know, you see it every day. What can be some of the catastrophic, problems that could leach into?
Sure. Well, one of the things we preach when we produce workshops and webinars and these types of conversations is one has to determine the acceptable, tolerable amount of residue on an assembly. One should factor in what's the cost of failure. That's the first question anyone should ask. What happens if this board fails? If in our live presentations, we have this video of a dog, and we show an electronic flea collar made by Hartz. And what's the cost of failure of the electronic flea collar? And we have this dog just scratching himself like crazy, and that's the cost of failure, an itchy dog. And then we show an implantable defibrillator, a pacemaker. And what's the cost of failure of that? It's a trip in an ambulance or a big black limousine, none of which you want to go into. So one has to look at what the cost of failure is. And when, in a dramatic sense, if one has dendritic growth, which is quite common in these circumstances where too much residue is on the board and the board is exposed to enough moisture to cause that chemical reaction, then if this is a board in a guidance system on a cruise missile, the cruise missile might hit, a girls' school instead of a terrorist training camp, which would be devastating. If it's a pacemaker, it may fire when it's not supposed to. It may not fire when it is supposed to, or the battery may drain if it's a calf issue. All sorts of things can go wrong. And when things go wrong with a board, particularly if a board catches fire, which there's an irony there, because I live in a gated community, and our control system for our gates, I got a call from the guard. I'm on our HOA board. I got a call from the guard. Our board caught on fire. And sent me a picture of it. That's going to be in every presentation moving forward, because it's still, it landed at my house, right? So,
right.
And I'm guessing that probably had something to do with, the original board was not cleaned properly, and it sits outside in in a housing, but it's not climactically protected, and I'm sure that happened. But when boards catch fire, then the products they're in tend to catch fire. And we just had an issue, our industry just had an issue with BMW this year on their little electric cars, their whatever. I don't think it was the i8, whatever it's called. They're small electric cars. They were recalled this year. And this was in the mainstream press, and you and I never hear our industries in the mainstream press, right? Nobody has civilians don't have a clue what we do. So this was in I think it was in the Wall Street Journal or some other mainstream outlet, that they had to recall their cars because the car was detecting a problem with one of its control boards, and to protect worse things from happening, the car would shut down, just immediately shut down. Now imagine doing 80 miles an hour on the freeway on the fast lane or in the carpool lane, and your car shuts down, right?
Oh my gosh.
It would be quite dangerous. So they recalled thousands of cars. And the stated reason in the mainstream press was that they had a board which was not cleaned properly by their tier 2 supplier.
Oh my gosh. Did you feel completely see, I've been telling you.
I've been preaching this for years. This doesn't just happen in a vacuum. They're not theoretical problems. These are real problems that exist every day.
I had no idea that story. That's a great story. Oh my goodness. But yeah, I think the implications are there. And I think for our audience, obviously engineers, they're not assemblers or whatever, but I think one of the things I encourage people in our audience to do is to get inside of an assembly house, right? And see, do they have good cleaning processes in place, right? And that implication is big. And so you had shared with me a wild tale that you were involved in. So why don't we jump in and talk about, is the Montreal what?
Well, the Montreal Protocol was the treaty that created the no clean flux, basically.
Okay.
Because it got rid of the chemicals that were used to clean circuit boards. So are you referring to that?
So I just wanted you to set that up, that,
Okay.
you know, that back in 80s, 90s, when did that happen?
1989
Okay.
was the year of the protocol.
So moving towards environmental friendliness, because we used to use a lot of nasty solvents and chemicals that cleaned really well, but then they went down our drains and they were bad for our environment. So
Yeah, they actually went up the stack. That was the big problem.
They went up the
chlorinated
stack.
fluorocarbons. So trichloroethane, 1,1,1 trichloroethane, Freon, TMS. These were two solvents that boiled at very low temperatures. They would boil at about 105 degrees Fahrenheit.
Mm-hmm.
So they would be boiling in these vats, and the boards would be put in a basket, be boiled in the solvent, and then the solvent would evaporate and turn into a vapor as it was evaporating, and then it would be rinsed effectively in the vapor zone. And then there were these condensing coils that were supposed to recondense and redistill the solvent, put them back down so nothing escaped. But every time you pulled a load of boards out, all the solvent went with it. And
oh, goodness. Okay.
the chlorine molecules were like Pac-Man. They were going up into the upper atmosphere and chewing on ozone. So, right now, our biggest, environmental catchphrase is either climate change or global warming.
Mm-hmm.
Back then, it was ozone depletion.
Yep.
80s. That was the big thing.
The hole in the ozone. Yep.
Hole in the ozone. We're all going to walk out and instantly get melanoma because, there's no ozone to filter the UV. So that was the big concern. These were ozone depleting chemicals.
Okay. So that sets the back, and so the industry innovated, came up with, so this got ratified, so we all had to comply with it as an industry.
It was ratified. In fact, it was ratified by every member nation of the United Nations. It's 200, I think it was 211 at the time. Every nation in the world ratified it. And this was an environmental treaty. There's only 2 treaties in the entire world ratified by every UN member nation. One was the Geneva Convention and this.
Wild.
Now, today, compare that to today. We're not going to get into politics, but
yeah.
If we did a treaty that said, let's all agree the sun goes up in the morning and the sun goes down at night, we couldn't get everyone to agree to that. Right?
So true.
So it was significant.
Yeah. So that with the backdrop, that we move toward these no clean fluxes, which, why don't you talk about that for just a second? Do you really need to not clean no clean fluxes? Well, explain fluxes first and then talk about the no clean part, just to sit.
Well, flux is a mandatory requirement when you're soldering. When you're soldering anything, if you're soldering stained glass windows, if you're soldering copper pipe for plumbing, if you're soldering circuit boards, you need flux. And the purpose of flux is to provide a barrier to prevent oxidation. When metal gets hot, it forms oxidation. In a solder pot on a wave solder machine, that's called dross. In the metal founding, forging industry, it's called slag. If you're serving Thanksgiving dinner and you have your gravy bowl out for too long uncovered, it gets a skin on it. All that is oxidation. And the purpose of flux is to reduce the oxidation and other things, and help wetting and help prepare the surface and clean the surface so that it's more solderable. So historically, since the beginning of electronics, we've always removed that flux. There was no reason to keep it on. In fact, it was problematic if it was kept on. But the methods we used lately and through 1989 to remove it involved these solvents, which were being banned by all the nations of the world. Mm-hmm. So some assemblers switched to alternative solvents, more environmentally responsible solvents, which weren't as good. Because basically, if it works well and tastes good, it's bad for the environment or bad, right? So this was bad for the environment because it worked very well. And so they come up with other solutions. Some people switched to water-soluble fluxes. People who had to clean found a way. People who really didn't have to clean, they were offered an alternative, and that was the use of this flux whose promise, which was a valid promise at the time, was it leaves very little residue, it's invisible or nearly invisible, and whatever is there is inert. So it's not harmful, so you don't have to clean at all. And 3/4 of the industry, which represents class 1, class 2 assembly stuff, which basically is not high rel, it's not going into space or people, they all went, woohoo, we have a party. We just got rid of a whole process. We don't, we save money. We don't have to buy new equipment. We throw away the cleaners, and life was good for a lot of years. But what's happened? You know this as well as I do, Judy. What's happened to circuit boards? They've gotten denser. They've gotten smaller. We have smaller footprints with more components and bottom terminated components. What were these people thinking? I think people who designed components are proof that what happens to people, mothers don't tell them they love them enough. They just get angry and they come up with components that can't be soldered very easily or cleaned very easily. So we ended up with over time, miniaturization has affected boards. Everything is small. I'm looking into a camera the size of 3 postage stamps, side by side, and there's all sorts of very miniaturized components in there in a high density environment. So now that components are so close together, we used to have this much space.
Right.
Components. Now we have this much space.
Yeah. Lots of hiding places for the no clean flux.
Right. So I liken it to if you're in Grand Central Station and there's 2 people in it. There's probably never 2 people in it. There's 2 people in it. One person has Ebola. As long as you're 500 feet away from that person, you're probably pretty safe, right? So that contamination is not spreadable. If you're in Grand Central Station on a real day, a Friday afternoon, and you're shoulder to shoulder with people and one person has Ebola, then you're going to have thousands of people get sick just because of the proximity. And that's kind of similar on a circuit assembly, when the density, the space between conductors is minuscule. And a little bit of contamination, which would have been fine if the conductors were an inch apart, is now problematic when they're microns apart. And that's the issue that we have. So no clean was wonderful for 2 decades or more. It's become more problematic now. Not everyone can use no clean. And if I had my way, if I could get opinionated, I would say don't call it no clean flux because you're fooling yourself. Call it low residue flux. That's more accurate. Because just the fact that it says no clean on the label doesn't mean you don't clean it. I mean,
like it's a command, no cleaning.
It's like those instructions on your mattress, don't remove this label, it's probably in jail. It's like people read no clean and they hear don't clean. Well, no manufacturer of so-called no clean fluxes can say you don't have to clean it unless they know what's the cost of failure, how dense is the board, where's it going, all these, what's the residue tolerance basically. So consider it low residue. Maybe it's low enough that you don't need to clean it. That's a very successful strategy for a lot of assemblers. But our polls, we do polling, and our polls are skewed because we're a cleaning company, so people tend to respond to cleaning companies when they're cleaning. So our polls are definitely skewed, but they're still interesting. Our polls show that of all the people that are running no clean, of our customer base that are running no clean, and we have 4,000 plus customers, that 55% of them are cleaning the no clean. 55%. That's more than half of our customers that are running no clean are cleaning the no clean. And people say, well, why would you clean no clean? Well, it makes sense because no clean fluxes are predominant. They're the most popular flux made. Rather than running a different type of flux just because you're going to clean it, run everything no clean. Don't clean what needs to be cleaned, what doesn't need to be cleaned, and clean what needs to be cleaned. You don't have to change fluxes. We can clean no cleans. Anyone can clean no cleans. So clean them if the board cannot tolerate the totality of the residues, not just the no clean residue, everything else. Because when you stop cleaning flux, you stop cleaning everything. All the stuff you left on the board in fabrication is still there. All the Dorito effect, the lubrication from the chains on the conveyors that the board went through, the operator's salty hands, whatever.
I wonder if you made the bare boards in Alabama and it's 90% humidity while we're laminating these things together and we didn't bake them. There's moisture.
Baking is huge. We're in the cleaning business. We're not in the baking business, but baking can solve a lot of problems. In fact, I I worked a few years ago as an expert witness in a civil litigation case that could have been solved by a mere bakeout problem.
Okay, so let's talk about that litigation case. It's a perfect segue. So tell us that story, because it's very telling, and it's better than just ranting. It really demonstrates everything you're talking about here.
So one day I get this call, and it came up on my phone, so-and-so attorney at law. Like, what's this about?
do?
Right? IRS attorneys, doctors, you don't want to get phone calls from them, right? So I answered it, and he said, I found you on LinkedIn, or I don't know. He found me on Google or some whatever. And I'd written a lot of articles on residue caused failure mechanisms. And he says, we have a case we're working. We're defending a company that's being sued by an OEM. They're a contract manufacturer. They have an OEM, and they took a project, and the boards went south, and the product went south, and they're now being sued, and we need your help. So I'm like, sure, this sounds fun. So it's not often I get to talk about ECM and contamination and gas
in a court of law,
cocktail parties, and people, right? But this is people that wanted to pay to hear this. So I'm like, yeah, let's party. So I signed on to that team, and long story short, the OEM had this great idea. They had the intellectual property, and they had the concept, but they didn't have the wherewithal to produce it. They were good designers, but that they didn't have any equipment to put anything together. So, and they didn't have any money. So, what do you do when you have a good idea and you're in the high-tech industry? You go to venture capitalists. So they went to the VCs, and they raised a bunch of money. And with that money, they were able to hire a contract manufacturer, which was the lawyer's client. And the OEM basically said, well, we want you to build this product for us, and here's the statement of work. And there wasn't a lot of specificity in that statement of work. It was to give you an example, they wanted the contract manufacturer to do everything. They wanted them to actually go out and buy the bare boards and just figure that out. And under material, it said down and dirty FR4, nothing special. That was verbatim. Down and dirty FR4. Now, I've seen a few slash sheets in my days, and I've never seen down and dirty, right? Or nothing
that
special.
Is not a brand.
It's not a brand, and it's not a configuration. It's not a material set. So FR4 is, but that just, that phrase came back to haunt them, because that kind of laid the groundwork for, we don't really care. We just give us something. And they built these boards. They were multi-layer boards. The boards were going to be operated by a battery, because they were going into the ground for a specific purpose. And they would detect things and send a radio signal up to a receiver nearby that was plugged into a power source. So these sensor modules had to last for 10 years. The battery was a 10-year battery. And they were put in all sorts of locations throughout North America underground. And after about 6 months, they stopped sending a signal. The batteries were failing in mass numbers. And they dug them out of the ground and sent them to failure analysis labs. And it was determined that there were several problems. There was corrosion on the board, and corrosion requires moisture. There was dendritic growth on the surface, ECM on the surface of the board, which tells us that there was too much residue left on the board. And most predominantly, there was CAF. There was this conductive anodic filament growing in the layers of the board. So the boards were cross-sectioned, and they spent a lot of money figuring out what was going wrong, and they found out that the boards had these little microcracks or dry weave, and the Plating Solutions was exploiting it, as I explained earlier. And so the OEM sued the contract manufacturer. They said, okay, you're responsible. And the contract manufacturer held up the statement of work and said, well, we did everything you told us to do, which was to reflow the boards with water-soluble flux and wash them in an inline cleaner using just water. Well, what's wrong with that? Well, what about the other contaminant species that are on the board, from board fab, from fingers, from everything? There's two types of contaminants that live on a board, polar and nonpolar. Polar is is soluble in water. Nonpolar is not soluble in water. They were only cleaning with water, so they only removed half the species, and they left the other half on. Then they had to hand solder this component onto the board using no clean flux. And it was like their brother-in-law was in the flux business, because they had these squeeze bottles, and they just oozed on. It was like they were decorating cakes, right? They just oozed on the flux and then touched up a couple areas that needed to be touched up, leaving all this unactivated no clean flux. No clean flux requires activation. We're supposed to burn off all the activators through the reflow process, through the heat. They didn't give it that. They left it on the board. And then they potted the board in silicone. And they thought that, it doesn't matter how clean we get it, because we're going to pot it in silicone. And when we pot it in silicone, it's not going to get moisture from the outside world. It'll be protected, which was good logic.
Yeah.
However, what they ended up doing, it looked like, when I was a kid, King Tut came around. You probably remember that.
I remember that.
King Tut came around, and here's this sarcophagus, and they opened it up, and everything he was buried with is still in there. Well, that's what happened to this assembly. The sins of the process, the moisture from no bakeout, the flux, the all the different types of contaminant species, the plating solution between the layers of the board, were all left on and in the board, and then it was sealed shut.
Oh, all the evidence was preserved.
Totally preserved, and it couldn't get out.
It was encapsulated. It was completely.
So basically, they just put all the bad actors in one room, closed the door, and buried them in the ground. And they did what they do. They acted bad, and they had to recall over 50,000 units, and all over North America. So it was this huge lawsuit. And when it comes to CAF, if they had just baked the boards, they still would have had electrical current. They still would have had conductive corrosive material, but they wouldn't have the third leg of the catalyst required to generate CAF, which was moisture. So if they had just baked it and then potted it, they would have. Most of the boards would have survived. They would have still had some dendritic growth issues.
What was the cost implication?
I don't know.
Oh, you don't know what it settled at? I'm sure.
No, they wouldn't tell me the settlement. It did settle. And, the side I was on claimed they were happy. So I don't know. That could be bravado, or it could be they liked the settlement. I don't know. But I think both groups of lawyers were very happy, because that's who wins in these things. The litigants don't win.
No.
It's you either lose or you lose more, right?
Yeah.
If you win, you lose. If you lose more. And all of this could have been solved with just a best practice approach. If you're going to use no clean, make sure it's properly activated. If you're going to clean, if you're going to go through a cleaning process, use a cleaning process that gets both polarities off the board, polar and nonpolar. You just do it right. And best practice before you coat or pot is baking. Bake them. Baking costs time, doesn't cost money. But one thing we found when we were going through the discovery phase, we subpoenaed all the emails and all the correspondence, and we looked through thousands of pages of that. And we found that there was significant pressure from their investors, from the venture capitalists, to ship. And they were falling behind in their shipments. And they were told, just ship. And if that is your primary focus, just get product out the door, then quality wanes and reliability suffers.
Yeah.
And so instead of spending an extra 2 hours in a bakeout process, which really costs nothing, just time, and eventually they all ship, they didn't have time for it. So it's the old adage, we don't have time to do it right, but we'll find the time to do it over. Right?
I always say, slow down to hurry up.
That's right.
That's the thing, right? And so how does IPC, what standards are in place that help protect our poor designers who are like a deer in the headlights thinking about this right now on some board they might design? Are there specific IPC standards in place about cleanliness?
Well, yes, there's standards on cleanliness, which just got changed last October after decades of producing a number. So there was always a number tied to a ROSE tester, a resistivity of solvent extract tester. You were allowed 1.56 micrograms of sodium equivalent on a board, or 10 micrograms per square inch. I'll use 10. And so, little over 10 is a fail, a little under 10 is a pass. And those standards were designed in the 70s. They were designed
Wow.
when, going to work with their 8 tracks in their car and listening to Bee Gees. And, that was when the standards were produced. And they'd never changed up until last October. And they were wildly obsolete because who can tell you 10 unless they ask you a bunch of questions? How clean should my board be? Well, 10. Well, wait, where's the board going? It's going in a person. Okay, 5. Wait a minute, where's it going? It's going in a missile. No, 2. I mean, they had 10 applied to everything. So
wow,
that was way obsolete. And so what IPC has finally done, much to the credit of Doug Pauls, who was the chair of the IPC subcommittee, that and his what he calls the Rhino team, who came out with the new standard, is they basically came up with a fancy way of saying it depends, which is the most perfect answer that nobody ever wants to hear. How clean is clean enough? It depends. And they told you how to determine what the number is. So they basically require that you test the board under current, under heat and humidity in an environmental chamber, get a surface insulation resistance number, do a rose test to correlate the rose test to that. And if you can prove your board doesn't fail after so many hours in a harsh condition under current, then that is clean enough for your board. And the next person might have a different number that they have to achieve because the number that you got might be creating failures on another person if they hit that number. They have to get a different number. So basically, it's an objective evidence standard that's now required.
Well, that's good. I don't know. Our standards, sometimes they do way outlive where the technology is gone. So what are, 1 or 2 key takeaways? You're a designer. You use EMS companies to get your product made. What should they be looking for in the form of, say, a supply chain partner, or, what should they be demanding in form of, cleanliness, or how can they get educated? What are some takeaways you might offer?
Well, I think one has to look at what the actual end product is going to be doing, what's its level of criticality, its cost of failure, what's its end-use climactic environment, and incorporate all those factors into the specifications that they give their contractors, right down to the board fabricators. And there are, continuing the example of CAF, there are CAF-resistant board materials out there that are known to resist CAF more than just standard FR4s, down and dirty, nothing special FR4s. So, if the board is going to be going in a place where it's not easily retrievable and it's going to be subject to a harsh environment, maybe one might consider a more CAF-resistant material. If there are subjects that there are conversations and opinions that talk about anodic vias versus cathodic vias, which one is better for CAF protection? There's plenty of articles on that people can Google and find out. There's design criteria and spacing on large conductors and high voltage areas of the board. The more spacing you have between conductors, the more residue tolerance between that space is provided. There's all sorts of things. There are third-party companies that will look at your design files, Gerber files or whatever type of files they're looking at, that will run it through an algorithm and determine its propensity for failure with residues.
I have a friend, Isaac Bott, who has BQR, which is reliability software that can do that, right? And
right.
It has those algorithms, right?
Right. If failure means increased business, planned obsolescence, then avoid that stuff. That's great. If failure means death and destruction or loss of reputation or litigation, all bad, then consider the cost of failure. Consider the assembly's tolerance for residues and errors in the design of the board. Put yourself. Our industry lately has migrated to the edge of the envelope. We are building boards today at the very edge of the envelope. Our
edge.
Toes are hanging over the edge. And normally what happens is technology catches up, methods catch up, and then we find ourselves in the center, and eventually we move back toward the edge again. And right now, we've been at the edge for a long time and getting nudged further to the edge. There doesn't seem to be a reprieve. Technology is advancing faster than we can figure out a way to build it and implement it. So that, boards are expected by our customers. We're in a tough industry. You and I both in a tough industry because our end customers, where these products finally go, build products that every year are expected to be half the size, twice as fast, last twice as long, and cost half as much. Almost year over year over year over year. So, the fact that it could be a cheap product, I'm looking into a $200 camera, which 30 years ago would have been a $1,000 camera.
Yeah.
But I don't expect that will ever fail. If I can spend $8 on it, and if it failed, I'd be disappointed. I'd be ranting about it. People expect electronics to last forever, and they don't expect it to break. And I didn't expect our gate controller to catch fire this morning. And if someone, I'm sure there's several thousand people in a BMW that didn't expect the car to shut down, and that was all the result of something completely preventable.
It's wild. It all boils down to clean boards. So I hope our listeners' minds are blown a little bit, rightfully, because this is one of those sort of invisible things, unless you listen to Mike's podcast and you're really on the ball, we don't hear a lot about. But Mike, I really want to thank you for joining me, because I know that you have been at work not only doing a podcast, but also putting out webinars and materials on your website and all that, and really providing quality education for whoever wants it. And so
have you.
Thank you. And I think that we have to. I mean, there is no time for engineers to go lollygagging around, learning about cleaning products and whatever it is we're talking about, right? The education needs to come to the designers these days. And I'm glad we both have the privilege and honor to do that. And I will be sure to share all of the good stuff that you put out in the education, and really appreciate what you're doing for the industry. I know it's good for your business, but it's also really good for the industry. So thank you for your generosity and your podcast and everything you're doing.
Well, thanks. I love listening to your show. I learn about board fab stuff that I didn't know much about it to begin with. So everything that you guys talk about is a good learning experience for me. I definitely get a lot out of your show. And thanks for having me on as a guest.
Yeah, my pleasure. Well, keep up the good work, my podcast brother.
Brothers in arms, yes.
Brothers in arms.
Yes. Nice talking to you, Judy.
Nice talking to you. And to our listeners, thanks so much for joining myself and Mike Konrad today. I hope you enjoyed learning about this unusual but it's very interesting topic. And make sure to check out the show notes below for links where you can go and learn more. Thank you for listening today. We love being with you. We'll see you next time. Until then, remember to always stay on track.